So testing 1, 2. Okay. Welcome back to the lecture. So yeah, I got some feedback from Ling, right? I mean, just some feedback. So so if I irritate you last week, okay, so I will say sorry to you, but the anger is not for you, it's for me, okay, because I feel like I can't really help your class, right? What do I mean by can't help your class? I try a lot of methods to make you feel appreciate pure maths, but I think I still can't reach what I want to get, right? At least from your assignment feedback, okay? For your assignment, when I read your assignment, where I mark your assignment, I will know how you study and what's your understanding, okay, towards the subject. So that's the point I not happy about. But I'm not happy about you personally, but it's the attitude. Okay. So I do really hope that you will change your study attitude. If you don't want to change according to my advice, it's fine. But you definitely have to change your attitude. Okay. Your attitude about study. Okay. Please be serious. Yeah. Okay, yeah. Please be serious. Um and so yeah. So the anger is not on you. Okay, so don't worry. And so um so I mean the assignment is hard. Okay, actually this part is hard. Like what I told Ming Xiu before. Mm, in my uni, right, even master students come to audit the class, or they take the class. So it's like the other students come to our uni do master. Maybe their undergrad doesn't have these courses, or these courses are not strong enough. They have to take abstract algebra. Okay. So meaning what? Meaning this course is hard. Okay, this course is really hard. But it's not to the stage that it's not doable. Okay. So I guess for me, what I feel is I feel blessed with this course. Okay. Because what to say? Because I appreciate. So it's like I appreciate. I hope you also appreciate. Because you won't get this kind of thing easily from other places. Yeah. Seriously. Okay. Yeah. I mean, if you choose not to do, it's your choice. But please don't sabotage me. That's all. Okay, please don't sabotage me. You can choose not to do, but please don't sabotage me. Yeah. Sabotage. Anyone know what sabotage? It's like 污蔑. It's okay. It's okay. It's okay. It's okay. If you don't do, it's okay. Yeah. No need to like take the responsibility. If you don't do, good. Very good. Okay. But just I want to say don't sabotage me. Okay. If you want to say bad thing about me, just directly talk to me. Don't talk at the back. Okay. Talk to me. Tell me. Talk to me. And then we can work something out. Okay. Yeah. So I mean, I really need to be changed or what? Okay, we can talk. Okay, or not? Yeah. Yeah. So don't let bitterness to how to say fill your life. Okay. Otherwise, it's not. I won't leave hard. You are the one who leave hard. Okay. Yeah. You know what's bitterness? Huh? What's bitterness? 可怜 not 可怜 it's your 怨恨苦毒 okay if you keep this in your heart others cannot help you only you can try and relieve yourself right do not let the sun go down upon your wrath okay you can be angry but try to keep it before sunset okay 不要生气一整天 okay 这下就好 yeah okay okay because if you keep how's that affected emotionally then it's hard to go on and I set the assignment hard and I also set a helping time so please come make an effort to come okay, I know you have your own plan but make an effort otherwise I cannot help you seriously yeah please make an effort I also make an effort we together make an effort okay I hope I make myself clear yeah okay very good question very important question when's the midterm okay how about we set our midterm at week 8 Monday week 8 Monday now this week is week 6 okay and then you will submit your assignment on Thursday so I'll give you feedback next week and then you have 1 week to do revision do tutorial and then week 8 we have exam is it okay okay or no week 8 Monday okay and then you can bring if you like you can bring calculator but I think it's useless yeah of course don't cheat using your calculator and then you can bring one double-sided A4 handwritten cheat sheet okay handwritten only please don't print it out if you print it out I will just confiscate it and then you will do without cheat sheet okay so I will make announcement on Moodle also written announcement yeah okay okay let's start where's my screen okay let's start with where we stopped last time so we are at the mid of showing every left coset of H and G is a right coset. Right coset implies for all G in G, GH is equal to HG. Okay. Anything wrong with this statement or not? I said that this statement is not complete. Okay, because I didn't tell you what is H and G. So I should tell you what is H and G. So let H be a subgroup of G. Okay. But G is a group. So now all the statement will make sense because I have a group, I have a subgroup. With a subgroup, I can build a coset. AH. So these two sentences, the difference is for the first statement, the left coset of H doesn't necessarily be the right coset that's built by the same G. Okay, so for example, maybe AH equals to HB. Okay. for the first example here. But it says that it implies that actually A has to be equal to B. Okay, A has to be equal to B. So why? Anyone thought about it? Why A has to equal to B? Anyone thought about it? Actually, I already released the answer in the lecture notes. Why does A have to be equal to B? Okay, so let's try and prove it. So suppose AH equals to HB. Okay, what do we want to show? We want to show that A actually equals to B. Okay, so there's one element you can take a look. So what are the elements in AH? There's a special element here you can take, which is just A. Okay, why? A because A is equal to A times E. E is an identity. Subgroups must contain the identity. So A is in AH. But what do you know? What else do you know? The right coset partitions the group. What does it mean by partition the group? G. What does it mean by partition the group G? Meaning what? Every element in G lives in one and only one right coset. Okay. So if your partition, whenever I talk about partition in your mind, straight away you should come up with a cake cutting, right? Okay, partition your G. Your A live in only one and only one of them. One and only one right coset here. Okay. So in particular, which right coset it live in? A live in which right coset? Huh? Right coset. Which right coset? A live in G, but which right coset? HA, HB, HC, HE, which one? Huh? Which one, Michelle? HA. Why? Because we can write A equals to E times A. Right? Okay. Okay. So if A live in HA, A also live in AH, okay, where AH equals to HB. Okay, this means what? This means what? A live in two cosets now. Can these two cosets be different or not? Huh? Can these two right cosets can be different or not? No, right? Then HA must equal to HB. Why? Because what? Because A must lie in one and only one right coset. Why? Because right coset partition the group. This is the definition of partition. Okay. Okay, so if you have two right coset intersecting, okay, HA and HB. Really, the right picture is just a single HA. Okay. So there should be nothing out here already. Nothing. Okay, they have to be the same, right, folks? Okay. Does it make sense or not? This is the meaning of partition. You have to get the idea of partition. Okay. Need to get the right idea for partition. Okay, what's partition? Imagine a cake, you cut it, okay, into portion, right? So your portion is yours, right? It's not belong to your friends. Right? Why you smile? I don't know. You guys like how's it? It's okay. Sometimes when how's it? Sometimes when I'm not serious, you become serious. When I'm serious, you are not serious. So we are like always out of sync one. Yeah. Okay, that's fine. That's fine. Dynamic is better. Just follow your heart. Okay, just follow your heart. But I mean, it's a kind of interesting experience with you guys. But anyway, we have how many weeks to go? 9 more weeks. 9 more weeks. Okay. Yeah, we should enjoy this 9 weeks. Okay. Next sem. Okay. Hey, what's the what course you guys have to take next semester? Just G. Hey, wait, what? All GE? Also no more fixed mathematics course you need to take. Okay. Okay, good. So you guys should choose your own path next semester. Okay. Yeah. So this one done. So this one done. Okay. So another one we want to check is about this theorem here. If a group G has just only one subgroup H of order R, okay, then the subgroup, that particular subgroup is actually normal. And I will also try attempt it last time before we leave. Okay, so let's start from proposition 1. So last time I discussed about proposition 1, where you can prove by using or proof version 1, or you can prove first way to prove it is to show using definition of subgroup. Okay, so definition of subgroup is what? So you check closure, check inverse, check identity. Okay, so this should be really familiar to you now. If not, please come get help. And then the second part is show that the subgroup is normal. Okay, if it is the only subgroup of the same order in G. Okay, and then we're also saying you can use part A, right? Okay, you consider GHG inverse. And then GHG inverse give you another subgroup because part A says that it's a subgroup. But the claim is GHG inverse has the same order with H. Why? Why is it the same order? Okay. Remember in this class, when we want to show same order, right? What do we do? What is the map we look at? Bijection. Okay. So is there a bijection between H and G inverse? Is there a bijection between H and GH inverse? Well, is there a bijection between GH inverse? Okay, so this is what we're gonna do here. So we're gonna form this bijection here. And what is hiding inside this notation here? This is an isomorphism. Okay, meaning I not just one bijection. Actually, this bijection can be upgraded to a group homomorphism. Okay, respecting the multiplicative property. Okay. So so what's the map here? So this is a map phi g. Again, phi little g. Okay, where I send x to gx g inverse. Okay. So there's a name for this actually. Okay. So we first, okay, so next we're gonna show phi g is an isomorphism. There's a name for this. This is actually a automorphism. Okay. Why we call it an automorphism? Because it is an isomorphism between the same group, G to itself. I we call it an automorphism. Yeah. If it is the same G, we call it an automorphism. Isomorphic to itself. Of course, it's equal, right? But yeah. Of G equals to G. Okay. So we want to show that phi G is an isomorphism. Okay. So how to show phi G is an isomorphism? So first you need to check it is actually a homomorphism. Okay. Phi G is a homomorphism. Okay, so how to check phi G is homomorphism? I'm Pishon. How to check something is a homomorphism? Don't remember. Definition, very important. Okay, look back to the definition. Remember how to show something is a homomorphism? Okay, good. So phi G of AB equals to phi GA times phi GB. Okay, so for every AB in your group G. Okay, so what's the left hand side? Phi GAB is what? Under this map here. What do you get? Wizard. So what's the image of AB under phi? Where does AB get sent to? When x equals to AB, what's the image here? G x AB, yeah, good. So GAB, G inverse, good. Okay, good. Okay, but on the right hand side, what do you have? On the right hand side, what do you have? Let me check one person. Raylan, you just came in, is it? You know what happened? You know what's going on? Don't know? Okay. Okay, so how about you? I find you first. Okay, so let's define phi G from the group G to G, right? Okay, by sending an element in X to GX G inverse. Okay, so this is phi G. Okay, tell me what is phi GA? Where does A go? where should A go? Under what's the image of A under the map Fiji? Good. G inverse. How about phi B? G inverse. Good. So is the middle equalities here hold or not? Why? G inverse G is the identity. Correct or not? Okay. So since phi GAB equals to phi GA times phi GB, this is an homomorphism. Okay. All right. Okay. So homomorphism done. How about bijective? Okay. How about bijective? Phi G is invertible. So there are two ways, right? One way is to show it is 1-to-1 and onto. The other way is produce the inverse for me and then check the two direction inverse, left inverse and right inverse. Okay, so which one you want to do? Huh? You want to produce inverse or you want to check 1-to-1 and onto? Check 1-to-1 and onto? Okay, so let's check if phi G is 1-to-1. And B is onto. Okay, so how to check 1-to-1? Suppose phi GA equals to phi GB. Okay, suppose the image is the same. You want to show that the pre-image is actually also the same. Okay, so phi GA equals to phi GB means what? GA G inverse equals to GB G inverse, right? Okay, does this imply A equals to B or not? No. Why? Use what? Use inverse. In other words, what is that? What law? Cancellation law. Okay, cancellation law. So you need to use twice cancellation law. So you cancel the G first, and then you cancel the G inverse. Okay. So what do you do when you cancel? You multiply by G inverse on the left, multiply by G on the right. Okay. So this is 1-to-1. How about onto? Suppose B is in G, right? Want to show there exists an A such that phi G A equals to B. Okay. Do you know what A you need to take? Take A is equal to what? Huh? Means you, what do you think? G, B, G inverse. G, B, G inverse. Okay, so let's check. So check where phi G of A equals to phi G, G, B, G inverse. Right. So what is phi G of that? Phi G of that is what? G of that thing, G, B, G inverse. Is this what you want? Huh? So, but you want to get B, right? Okay, but this case you get G squared BG minus 2. So it's not possible. Okay, so what you need to do? You swap. Okay, so instead of taking G inverse, you take G inverse BG. Okay, so in this case here, what happened? So that you can cancel with the G from your conjugation map. Okay. Okay, now. Yeah. Sorry. Try to find the inverse. Or you want to try second method as well? Okay. Okay, let's try second method. Yeah, let's try second method. Okay, so first method done. Everyone happy or not? Show how to show 1 to 1 and 1 to. Everyone happy? Happy? Okay. So let's do the second one. Okay. How to find for the second way? Find inverse of Fiji. Okay. So inverse of Fiji is what we call Fiji to inverse. Okay, find this. So what's the candidate here? How do you find? How do you define Fiji inverse? So this guy here need to satisfy the inverse property. That is, it is a right inverse. It is a left inverse. It is also a right inverse. Okay. Maybe I use identity here because this is a function, identity function. So what kind of a map you want to choose? So this is equality on function, right? So you need to check on all. Let's fix x now. Okay, x in G. So you need to check it on all x. Okay. So let's say if I apply Fiji to my x, let's see what I need to do to get my x back. So I have G x G inverse here. What do you need to do to get your x back? Okay. So this should somehow shed some light on how to define Fiji inverse. Okay. What does Fiji inverse have to do to GX G inverse to get your x back? Any idea? Huh? G inverse G, right? Huh? Right. So what do you do? So actually you define phi G inverse as what? Phi of G inverse. Okay. What does this mean? This is a map from G to G. Okay. Where you send x to G inverse x, G inverse inverse. Right. Which is, in other words, G inverse x G. Okay. Why does this work? Because if I apply P of G inverse, okay, on phi G, I'll get G inverse of G x G inverse G. Okay. So in this way, you can use associative law to get rid of the G inverse G, and then you get x. Okay. So then this will become a identity map because you send all the x to x. Okay. You should check the other direction as well, right? Check the right direction. So the right direction, what do you get? You get G inverse x G first, okay? And then you conjugate it. G inverse x G of G inverse. Similarly, you will get x again. So what's the difference between these two? Really, you are using the strength of inverse. Okay, the first one you have right inverse. Oh, sorry, left inverse cancelling. The other one you have right inverse cancelling. Okay, so you are using the full strength of the person. Yep. Say again. When can we assume? You mean why we define like this? Because this is your job. You need to find me the inverse. Get me the inverse. This is your choice now. You need to show an inverse that works. Yes. Because what does it mean by an element to be invertible? There exists an x inverse such that x inverse is identity, x inverse x is also identity. There exists So that exists means you need to find one. Okay. For the statement that there exists, you need to find one. Okay. So the inverse of PG is you need to find me one that works. Understand? Find the inverse of PG so that this equation holds. Okay, so that this equation holds. Because this is the definition of something is invertible. Okay. Yeah, that exists. Cannot. Yeah. 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 Oh yeah, good. So wait. Okay, good. I will address that question, but we haven't finished here yet. Okay, so I just show you that this inverse is the inverse, right? But is it a homomorphism? I would say that it's clear from my construction, or it is automatic from my construction. Okay, because my construction here, I use G inverse G. But what I showed just now is phi G is a homomorphism for every G, in particular for G inverse. Okay. So this proof here, okay, this proof here works for all G. Okay, in particular G inverse. In particular for G inverse. Okay. Okay. Does it make sense? Okay. The proof that phi G is an homomorphism is true for every G you pick. In particular for the G I picked just now, phi G inverse. Okay. Okay, so this is a difference for all and there exists. If it's for all, any element from the same set works. If there exists, you need to find one. Okay. So here I would say that, not that, PG inverse is a homomorphism which is clear from the construction. As PG is a homomorphism for all G in the group. Okay. Yeah. Usually no one wrote the last line already. They just say clear from construction. So whenever you see the book say clear from construction, you should look back what they constructed. Okay. So just now Soning saying, hey, we just look at X, why you do on G. Okay, so actually I do something extra already. So this is an automorphism on G. It's also an automorphism on wait, let me think. On okay, not on H yet because we don't know whether it's normal, but it's an automorphism on G. So what about H? What happened to H? H is just a subgroup of G. Okay. So what's VGH here? VG on H. Okay, this is a set. What is this set? This set can be written as GH G inverse. Okay. So this in particular, what I'm saying here is GH G inverse is an image of a homomorphism. So if you are an image of a homomorphism, that means you are a subgroup. Okay. So this is one way to prove part A. Okay, this is one way to prove part A. Okay. Because GHG inverse is an image of the, we will call it conjugation morphism. Okay, it's a conjugation morphism. It is an image of a homomorphism. Okay, right? It's an image under Fiji. Okay, it's an image under Fiji. So it's a subgroup. And then, yeah, this is one way to prove part one. And then we're gonna use this just now. We're going to say that actually H and GHG inverse has the same order. Okay, they are the same order. Okay. But the question said there's only one subgroup of such order. Okay. So the question said there's only one subgroup with the order of H. So if H has order R, GHG inverse also has order R, because we have a bijection between them. And there's only one subgroup with the same order. Meaning what? The two sets have to be the same. Okay? Meaning, let me write down. We know DH equals to GH inverse. Okay? If you really want to be rigorous, right, pedantic, right, you should show this. Okay? This is a subset inclusion. Right go to left, left go to right. Okay? Try and write it out as an exercise. We know that this is true since PG is an isomorphism. Or actually, we really just need a bijective for now. Bijective. No, isomorphism is good. So bijective and homomorphism. Okay, this means what? This means GH, G inverse, has the same order as H. Okay. Also, GH, G inverse is a subgroup of G. Okay. So it is a subgroup of the same order of H. But the question said there's only one such subgroup with the same order. So by assumption, there is only one, there's only one subgroup of order R, or okay, there's only one subgroup of order. Okay, let me see where's my, did I say what's H? Yeah. Okay. So there's only one subgroup of order equaling to the order of H. Okay, and GHG inverse is a subgroup of the same order. So this means that GHG inverse has to equal to H. If they are equal, then by proposition that we shown last time, what's the proposition? Let's take a look. From this proposition here, okay, we know that H is actually normal. Okay, maybe it's the first time you see this proposition, it's all right, but make it a second nature. Okay, make it a second nature. or by position, by previous position before. Actually, okay. Any question or not? Any question? Question? So this is what we want to prove if a group G has just one subgroup H of order R, then the subgroup is normal. Okay, any question? If not, let's take a break until 9:01. And the meantime, I will take attendance. Yeah. Until where? Until next week. Yeah. Because we're a bit delayed. Today we're a bit delayed. Until next week. I'll tell you I'll tell you where I want to stop. And then we will see. So actually this hour I want to cover correspondence theorem. But anyway, that's fine. So hopefully in next hour we cover this correspondence theorem. And then the plan I want to finish on week 6 is about finitely generated abelian. This is a part in the Raleigh, okay, section 9. So about this finitely generated abelian group, we will do just a few corollary and some more proof on product group, and then we will deduce this important result here. So every finitely generated abelian group is isomorphic to some direct product of cyclic group and Z. And then we will stop here. This is for midterm. Hopefully can be done by next Monday. Okay. Yeah. So the last part will end for section 2 is Frale section 9. Okay. Yeah. Okay. Hopefully will be done by next Monday. Any other question? Okay. Okay. Let's take the Venus. Venus, how are you on Monday? A bit sick. Okay. Okay. Please take care. A lot of people sick now. 乐天、伟泽、上颚、严苛 ，OK， 泽瑞、Raylan、思瑜、Seng、训林，为是海人啊，also sick 啊，海人啊，not contacting him， you got him， 金波、Y、B 酸、殷勤、可以、雪岩、家业、李凯、袁家、文硕、一定、玉伟、诺言、燕博、彭业、林金、Tuesday, sick as well. Sick 啊 Yeah. Please take care 啊。董洁、宜州 not here just today. 宜州、定宇、刘晴、曾腾、说你 B yes 千则线莹莹Grace Diet嘉文哎when 嘉文 walk in today I thought it's different people I recognize 林秀 Michelle Ryan Ellie where's Ellie coming traffic jam obviously 雪梅子源
我这两个问题，两个就是 H 和 K subgroups 和 G，它们交集会是空集。然后那么这两个 product 的 two elements 就是一定是属于它们的交集。
对啊，我们上个星期 prove 了
什么？
上个 assignment
上个 assignment
prove that the intersection of subgroup 是个 subgroup。
那就是 intersection，那我们只能说这一个是 subgroup。我的意思是 for all H。
哦，那当然不是喽，那当然不是哦。对啊，你可以找 counter example 啊，可以找 counter example 啊，说2z 和3z，2z 3z 没有 intersection，
2z 3z 有
6z 跟2z，嗯
6z 跟2z，那他们的交集就是6z。
确实，有想想，我们 counter example 啊，2是不是太大了？选6z 和10z， 6z 和10z 有没有交集？有交集，60在里面。然后你任意取两个，应该都在。
是
加进吧。
那这一个是，那就是存在这个样子。存在
存在。
就是改成存在的话，那么这个就成立了。
对啊，那你要这个什么来干嘛？我不知道。就存在啊，当然存在，因为你都 prove 了，只要是在它 intersection 里面的东西，这个东西都成立，对不对？只要 H 跟 K 都在它的 intersection 里面，这个东西就成立。哪里 loss？
这个是真理，
哪一个？怎么嘞？也可以拿来证 A。什么？哪一个？对，这个是拿来证 B 对，
这个开始几个
这个开始是 B，对，没错，全部塞在 B 也可以，都可以的，看你要怎么取。可以啊，可以塞在 B 啊，但是说，
可是这个是 for A，这个
A 也可以用，你要全部塞在 B。
OK，
这里边这个 two circle
对，
就是有没有办法表达成 product 两个 three circle？
好，这个是好问题，你想一下，three cycle 是什么？three cycle 是 even permutation，对不对？所以你看你是 even，这里呢 odd
even 有没有可能 odd？
even 可能什么？
有没有 even 的数字加起来会拿到 odd number？ 你这里只能够有 even 的 product 出现嘛？那这里是 odd 嘛？
对
odd 的 permutation 可不可以等于 even permutation？ 不可以了。可以了。对，但是我的那个题目不是 about 一个 transposition 哦，我的那个题目是 about alternating group。alternating group 里面都是 even。对啊。
对，他那个题目我是这样的思路，它不是
它最小的 non-trivial element 应该是至少是2个组成的。
对，就所以它里面的应该是由那个就是 even 的
对，
然后然后他要证明那个 it can be
generated by
traceable。
对，
所以我就是想让它变成2个这个，但是变不了的。
不能啊，但是它不是它的最小元素啊，在 alternating group 里面啊。对呀，你不可能这个东西不会单一存在在 alternating， 它肯定要 pair with 另外一个 transposition， 因为它里面都是 even， 一定是0、2、4、6、8个 product of transposition 嘛，最小的组成元素是2，你明白？比如说1、2、2、3啊，
对
，1、2、3、4啊，这样。这是最小的 non-trivial 的 element 在 alternating group， 下一个就要到4了，再下一个就要到6、8，你明白吗？所以最小元素不是它，其实是 non-trivial。对啊 ，trivial 的就是 identity 嘛，那个没有得做 ，identity 在所有的 cycle 里面，明白吗？所以你要解决的是这些东西怎么写成 product of 3 cycle， 明白吗？你只要会解决2个、4个，你就会解决；6个就会解决，8个也会解决。对，
我不会看一下。
这个是 adjective。就一个。
对。Okay. So is Kyron coming on? Is it? Okay. Okay. That's fine. Okay, so next part is about the correspondence theorem. Okay. Correspondence theorem. Correspondence theorem. So let's start with some motivation. Kind of abstract. So let's see how it goes. So similarly, we still have a group homomorphism. Okay. So why we look at group homomorphism? Because we want to look at how to compare different groups. Okay. So we compare different groups by using a map. Okay, a group homomorphism. So what can we do in this group homomorphism here? So we can restrict our map to a subgroup. Okay. So I don't look at the how phi apply on the whole G. I just look at a portion of G. But this portion is meaningful because it's still a group. Okay, in particular, it is a subset. So it's a subgroup. Okay. And then we can restrict our morphism to this group here. Okay, we just look at how phi add on this group. And then we look at the map as well. Okay, mapping to G prime. And then the claim is we can find, okay, we can find the kernel of this phi here, okay? Right, kernel of a homomorphism is always a subgroup. Okay, kernel of morphism. This is what we showed last time. Okay, so we have this. So we have produced a new kernel here. So can we describe about this kernel? What's the natural candidate for this kernel? Any natural candidate you can think about? So previously, phi, you also can find a kernel here. So kernel is in here. So kernel of phi. But can you relate kernel of phi to kernel of restricted phi or not? Any idea? Okay, so I mean, if you look at this picture, right, maybe you don't have any idea. You should think of it as a space. Group is a space, okay? And then inside G, you have H, okay? And then inside G, you also have a kernel of phi, right? So, wait, let me do a figure. Yeah, we have a kernel of phi somewhere. I don't know where is it. And inside H, we have kernel of phi restricted. So kernel. So G is not important now. So let's keep G small. G not important. So I have a G kernel of phi inverse. Can I relate these two things or not? Can I relate these two or not? How? Any idea? Jimbo, you got any idea? Anything you want to say? It's inside what? It's inside the kernel of phi. Okay, so in other words, meaning what? Actually, we have very strong result, that is, this kernel here is actually the original kernel intersect with H. Okay, so meaning what? Meaning this kernel of phi maybe somehow will cover this kernel here. Maybe you don't cover the whole H, but at least you need to contain the kernel of phi restricted. Okay, so this is a picture you need to keep in mind here. Okay, this is kind of strong result, and you can try and prove it. And then similar what? An image of a phi of H restricted to H is equal to just phi H. This one is obvious. Okay, but this kernel part is kind of strong. Later we'll see in the correspondence theorem. Okay. So actually it means what? You restrict your homomorphism to a subgroup. Where do you get the kernel? Actually, those kernels are part of the kernel of the original homomorphism. And how do you get it? You just take the original kernel, intersect with your domain, and then you will get the new kernel. It is equal, it is equal here. So two direction. If you evaluate all the elements on the left, it will go to 0. And all the elements that go to 0 is actually coming from the intersection. And this is the plane. Okay, this is the plane. Okay. Okay, so maybe let's go straight. So to prepare for the correspondence theorem, okay, we need to do some preparation first. So let's prove some proposition before we go to the theorem. Okay, so I keep this notation following the RT notation here. So let phi be a homomorphism of group. Okay, with kernel, let's call it K. Okay, and a subgroup in codomain. subgroup in code. Okay. So everyone can differentiate this number. So I mean alphabet. So I write normal alphabet with a script G. Then what happened? Then the kernel, okay, kernel is actually a subgroup of H, okay, where I define this H to be the inverse image of a subgroup. Okay, and obviously we have shown the inverse image of a subgroup is also a subgroup. Okay, and then 2, if, okay, if the subgroup we have in the codomain is normal, okay, then the pre-image is also normal. Okay, the pre-image is also normal. 3, if phi is a surjective map, okay, if phi is a surjective map, and the pre-image is normal, then the image is normal. Okay. And you see, I want you to see a pattern here. Whenever we talk about surjective, right, we like to deduce something on the codomain. This is the question I give you in the assignment, right? I have a surjective homomorphism from G to G prime. Show that if G is cyclic G prime, then G prime is cyclic. Show that G is abelian, G prime is abelian. So we have surjective map. I want the result on the codomain. Why? Because it is surjective. Surjective means what? Every element in the codomain has a pre-image. So I can study the codomain by pulling back to the domain. Okay. Use something that I know about domain to deduce things inside the codomain. Okay, that's why this statement here will make sense. Okay. All right. You want to prove this? Okay. Think about, maybe spend 2-3 minutes. Think about it. How you prove part 1? Yeah, questions? I'll throw out a bit, sorry. Yeah, sorry. Okay, so how to prove part 1? How to prove part 2? How to prove part 3? Okay, start one by one. So what's the thing you need to prove in part 1? What's the thing you need to prove in part 1? Actually, I think this is a subgroup, really. There are few things you need to see. So there are 2 segments here, right? So is this a subgroup or not? Is K a subgroup of H? Is H a subgroup of G? Okay. H is a subgroup of G. This one is what we have shown. Inverse image of a subgroup is a subgroup. How about this one? Is K a subgroup in H? What do you have to show it is a subgroup? You need to show a subset. And subset. Okay. Subset means what? Every element in K have to be in H. Okay. What are the elements in K? All the elements that evaluate to 0. In particular, these elements are the pre-image of identity. Is identity in H or not? H is a subgroup. So identity is in here. So K is just the pre-image of E.
Okay. So what have I said? So what have I said is K is the pre-image of the identity. Right. But identity is in H, always in H. Okay, now. So it's a subset and kernel from the subgroup. So it's a subgroup. Okay. Everyone following? Okay, to show something is a subgroup, you need to show two things. One, subset, two, groups. Okay, subset plus group. It's a subset because it's a pre-image of a single element E. It's a group because kernel is always a group. Form a group. So it's a subgroup. Does that make sense? Make sense? Can follow now. Please try and follow. It's not particularly hard. Please follow, okay? Yeah. Everyone happy with first one? Any question or not? Okay, with these two subgroups, we're done already. Okay. Okay with the two subgroup. Version. Following? No. Okay, very honest. So do you know why K is a subgroup of H? The pre-image. No. Think about it. The reason is K is a pre-image of the identity. Okay. So this part is to show K is a subgroup. Okay. How about this part here? Okay. If H, okay, in the image codomain is a subgroup, is a normal subgroup, then the pre-image is also a normal subgroup. So to show that the pre-image is a normal subgroup, what do you need to show? You need to show that every conjugation of the element here is inside H. Okay, so let's write down. So this means that for every G inverse is in H or equal to H. Okay. But what are the elements in H? These are the pre-image of H. Okay, these are the pre-image of H. So how about let's move this guy and then I'll try and show it. So this part we want to show that for every G in G, then G inverse is in H. Also for all H in H. Okay, this is what we want to show. To show something is a normal subgroup. So how do we do it? How do we do it? So what do we do? We know that these are the pre-image of something in G. Right? So in other words, in particular, G inverse equals to some, let's say H1, okay, H1, such that H1 is in the pre-image of something else. Okay, makes sense or not? Does it make sense? Because to say that an element is in H, okay, to say that an element is in H, you need to realize that element as some pre-image. This is the line you need to get. Okay. What is it to say it is in H? So you need to ask yourself, what is H?
X is a pre-image of some subgroup. Okay. So meaning what? Let me I'm just unfolding the definition. There's no much construction yet. So meaning there's this Z in H such that we map H1 to Z. Okay. To say that H1 is the pre-image, is in the pre-image set of H. Okay. Easy or not? Easy already. Okay. So what to do? So what can we do? We know about the normality on H. Okay. So in particular, we can apply phi GH G inverse. Okay. If this is equal, okay, let me write in other color. If this is equal for some Z in H, then we are done. Why? Because it is a pre-image of H. Okay, it is a pre-image of element in H. Right. I made phi inside H. This is the definition of pre-image. Okay. So if I can show that the image of GHG inverse is equal to some element in H, then I'm done. This is the definition of phi inverse. So I think I should remind you what is the inverse definition, inverse image definition. So what are these? What's this set here? This is called the inverse image of H. Okay, inverse image of H. So what are these? These are elements in where? In the domain. Okay, in the domain G, such that phi of X is in H. And this is what Li Kai told us last time. So if I can show that phi GH inverse equals to some element in H, then GHG inverse will be in the element set. Okay. Okay. All right. So is it true? So let's compute. Phi G inverse is what? By homomorphism, it is phi G phi H times phi G inverse. Okay. But we are not quite done yet. We need to use homomorphism again to write phi G phi H times phi G everything inverse. Okay. So the question is this guy in script H or not? Why? Yes, because this is a conjugate of phi H, and script H is, by assumption, it is normal. Okay, so this guy is in script H. So I have write that phi GHG inverse is equal to some element in H, meaning GHG inverse is in the inverse image. Okay, because it satisfies the definition of inverse image. Okay, phi X is equal to something in script H. So X is in the pre-image. Okay. So by definition, GH G inverse is in the phi inverse of H. which is just equals to H. So we have shown that if I have H in H, I have G inverse in H as well for all G. Okay, so H is, so hence H is normal. Okay. Yeah. Very important, this definition. You need to go back and revise. Okay. Inverse image. What is inverse image? What is image? What is pre-image? Okay. What is group? What is group homomorphism? Yeah. What things we use here? What thing do we use here? We just use the definition of normal. Then you need to know. If you don't know, you surely don't know what I'm doing. Normal subgroup. Inverse image. You need to know. What group homomorphism? You need to know. Property of group homomorphism. That's all. 3 things. There are 3 things in this proof. These 3 things you need to master. Yeah. If you don't understand the proof, go back and look at these 3 definitions and then come back again. Okay. Okay. How about the next one? The next one. Is this more obvious or not? So what do you want to show? Okay, let's write down what you want to show first. You want to show that the script F is normal in G. It's a subgroup. We already know. Okay, because this is given in the question. But how do we show this is normal? So similarly, for every, let's use P then. P in H, okay, and for every G in G, I will need to show that G, P, G inverse is in script H. Okay. But what can you do? What can you do? Subject, right? If it's subjective, pull it back. Okay, bring it back. Bring it back to G. Okay. Bring it back to G. So since P is subjective, there's this one. There's this, for example, H1, H2, such that P of H1 equals to G, P of H2 equals to P. Okay. Okay. So I bring all the elements back to the domain. Okay, pull it back. Okay. So to show that GPG inverse is in H, right? What do you need to show? This is the image under is an image under phi. Okay, it's an image under phi. So you need to find something that map to GPG inverse here. Okay. You need to find something that map to GPG inverse. So what's the thing you think that map to GPG inverse? Okay. So let's say I want this guy to be in H, meaning I want to get someone that is in H that sends to GPG inverse here. Does it make sense? I want to find some X such that phi of X is equal to GPG inverse. So what's the X I need to look for now? Okay. So this is like a reverse engineer. I'm doing reverse engineering. Okay. I know what I want to, where I want to go. I want to work backward. See what is my X. Okay. I'm doing reverse engineer here. So I can pull everything here back, right? Because this is phi is surjective. So I can get G to be phi of H1, and then P is phi of H2. And then how about G inverse? G inverse is just phi of H1, everything inverse. Okay. But Again, using a group homomorphism trick to combine this guy. Okay, so let's combine them. Before combining, I can bring my inverse in first. Okay, and then I combine them. Right, I got phi of something equals to something in H now. Right, but the thing is H1, H2 inverse in H or not? Is the guy inside in H? This is the question now. Is it in H or not? Right? Is it in H? And why? Why is it in H? H is normal. Sure, H is normal. So what? I mean, to talk about normal subgroup, you need to make sure that H2 is in H, H1 is in G. Okay. So is H2 in H or not? Is H2 in H? So where does this H1, H2 come from? Subject where? Subject on G. So this guy come from G, obviously. Is it coming from H or not? No. What is H? What is H? What is H? H is by definition what? Inverse image of the script H. You get what I mean or not? So you need to picture this. Picture. When I talk about group, draw a picture in your mind. Right. From calculus, I already draw a picture for you. So I have a G. Okay, I have a G. Okay. Where is H? H is inside here. Okay. What is the definition of H? Phi inverse of script H. Okay. What is inside here? You need to look at the codomain. This is a script G. Okay. And then you have a subgroup H. Okay. And then all the pre-image are the things that get mapped to the script H here. Can you see the picture? Can you understand the picture here? So what is pre-image? Pre-image are all the things in the domain that get mapped to the script H. Right? So this is the pre-image as inverse image of H. So in particular, when you want to find the pre-image of script H, where do you want to find? Exactly the inverse image set. Okay, so this H1, H2 is lying inside, by definition, the inverse image of H. This is by definition. Okay, understand? Definition. So if you really still don't know, confused about what I said, I'm keep telling the same thing. This is the definition of inverse image of a set. Please check out this definition. Okay, please check out this definition here. Inverse image of a set. Okay. So H2 is in H, H1 is in H, in particular is in G. Since H is normal, then H1, H2, H1 inverse is also in H. Okay, because H is normal and H2 is in H and H1 is in G. Okay. Okay. So we are done. We have found something in H that gets sent to GP G inverse. This is what we want to achieve. Okay. Yeah.
P. So okay, so P is a element in P H grid and yeah.
So like because H2 is the pre-image of P, therefore like H2 is of its
Inside of what?
the element of its. Can I say that?
Inside where?
It's
It's H. Yes, that's right. That's right. That's the definition. Yeah. So if you are a pre-image of something, so this H2 is a pre-image of P, H2 is in H. This is the definition, yes. So in particular, H1 also in the pre-image of script H, because you have this equation here. Okay. It's just a fancy name to talk about these two elements. This one is a pre-image, this one is the image. So G is the image of H1. H1 is the pre-image of G. Why is it pre-image? Because you apply by the map, you get the image. Pre-image, before the image. Before the image is H1. Okay, after you apply P, you get the image. Okay. Okay. Yeah. So two things very important in mathematics. Just now I tell Jia as well. So one thing is you need to comprehend. Second thing is you need to be able to convey. So how to convey? So this is the part, this is the accent of mathematics. You need to make precise. Everyone will know the precise language. But how you understand it, how everyone understands it might be different. But everyone should understand what is being written down. This is why maybe some of them will get good intuition because they have more understanding about it. But at the bottom, everyone should have at least the same understanding. And then those extra one will help you understand better the subject. Okay? Yeah. So since you understand better, right, you will create more language. Then people will try and learn that language. And then people will get better as well. So this is how knowledge works. Okay. Okay. Okay, about this. What time is it? Okay, still have time. Let's go on. So I will introduce this correspondence theorem. Correspondence theorem. Correspondence theorem. So from the last proposition, you will see that we have some surjective property in. So we need to have a surjective map first. Okay. With a kernel. Okay. Kernel is important. We want to describe this kernel here. And the result is there exists a bijective correspondence. Okay, there exists a bijective correspondence between a subgroup in the codomain with the subgroup of G. Okay, but not all the subgroup in the domain. Only those subgroup that contains the kernel. Okay. So if you have a surjective morphism, you really can study the subgroup inside the image. Study the subgroup inside the codomain using the subgroup inside the domain. But only those that contain the kernel. Okay, so what's the bijective correspondence here? So you can start with a subgroup inside your codomain. Okay, all of them. Okay, all of these will correspond to the subgroup of G that contain K. Okay, obviously what? Obviously, you should think that G is somehow smaller. Okay, the script G somehow smaller than G. Okay, because it's surjective. So somehow it's smaller. Okay, or at least as big. And we can study every subgroup inside my codomain. Okay, by looking at the subgroup in G, but not all of them. Only those subgroup that contain the kernel. Okay. Does it make sense or not? Must contain kernel, right? Because inverse image of the subgroup in G must contain the inverse image of identity. And the inverse image of the identity is precisely the kernel of the map. Right, this is what we discussed in the proposition just now. So what's in a symbol form? So you have a subgroup inside script G, okay? And all of these correspond to certain H in codomain. And then these H, right, need to satisfy a property that is it contains kernel. Okay. Yeah. So what's the map? What's the map? What's the correspondent here? You want to guess what's the correspondent here? If I have such H, how to find script H? If I start with such H, okay. So bijective correspondent here means I can find a bijective map, right? Okay. So give me a H here, I produce a script H here. Give me a script H here, I produce a H here. Okay. So if I give you the H here, how am I going to produce the script H? Sorry? Yes, the obvious things you should do is you just apply phi on this H. Just now we showed that this is a subgroup, right? Okay. This is easy. This is always a subgroup in G. Okay, this part is easy. Because image of a homomorphism is always a subgroup. How about going backward? If I give you a subgroup in the codomain, how do you produce me such H? Huh? How do you produce this H here? Obvious also. You just take the inverse image. Okay, not that I don't claim that phi is invertible. I didn't, so disclaimer here. I didn't say that phi might not be invertible. What am I writing here is phi, the inverse image of phi. Okay, I take all the pre-image of H. Okay, so here phi inverse is the here. Phi inverse is the inverse image. Okay. Or I can say more precisely, phi inverse of H is the inverse image of H. Okay. It's a set. It's not function. It's not taking inverse of H. It's an inverse image. Inverse and inverse image is different. You need to differentiate. So there's some terminology you want to differentiate here is inverse of a function is not equal to the inverse image of a function. Okay. This is something you need to take note. Okay, what's the definition of them? Find example why they are not the same. Okay. What else? So actually we are just collecting results from what we have shown just now. So more things to show is if H and H script are the corresponding subgroup. Okay, meaning you can use phi and phi inverse to connect them. Okay. Then what? Then H is normal in G if and only if the script H is normal as well in its group. Okay, and then we can know more about the cardinality here. We can know more.
if H and script H are again the corresponding subgroup, okay, then the cardinality of H is equals to the cardinality of script H times K. Okay. Yeah. So we have bijection between subgroups. What else we can do? Okay. We can check the normality. Okay, whether the subgroups are normal or not. Okay. Can I deduce the whether the subgroup is normal from the other group or not? Okay, I can. Okay, through this. What else? I can deduce the cardinality of the subgroup. Okay. So if you're interested with H script, then you need to know about the cardinality of H and K. Okay, either one of them you don't know, but you know the other two, you will get the answer. Okay. What time is it? Okay, let's talk about what we need to prove, and then we will decide whether we want to prove or not. So what should we prove? There are a few points here. There are a few points going on here. Okay. There are a few points going on here, but let's set the assumption first. So what do we have? We know that K is a normal subgroup in H, okay, which is in G. Then we also have arbitrary subgroup in the codomain script H in the script G. Okay, what we need to check. So if we want to claim this MAT is a bijective correspondent, first thing we need to show that phi H is a subgroup. But this one we already know is an image of a group, which is a subgroup. Okay. And then phi inverse is a subgroup. We know that it's a subgroup because it is a pre-image, okay, of a homomorphism. Why does it contain K? Because K is precisely the pre-image of the identity element. And the identity elements live in the subgroup. Okay, so what am I talking about? So I'm talking about phi inverse of H. Okay, phi inverse of H contain phi inverse of E, which is equal to K. Okay. So first thing we establish is image of a homomorphism is a subgroup. It's a subgroup of G. And then the second thing we establish is the E inverse image of homomorphism is also a subgroup. And moreover, this guy contains K. And this guy contains K because it contains pre-image of all elements in H. In particular, it contains the pre-image of an identity element. And then this is by definition K. Okay? Or you can show that actually is equal to K. Okay, so this is how we show the bijective correspondent. Next part, we need to deal with the normal part. Okay, so this means we need to prove that if H is normal in G, if and only if phi inverse of H is normal in G. Okay, so how do we show this? This is done by the proposition just now. Done by proposition. Okay, previous proposition, where we have the condition on surjectivity, homomorphism, and then we can use the normality of G to deduce the normality on script H. And then the other direction, you don't need surjectivity. Okay, one direction you don't need surjectivity. The other direction you need surjectivity. Okay, if you go from domain to codomain, you need to use surjectivity. But if you go from codomain to domain, you don't need surjectivity. Okay, so this is the extent of the proposition just now. Okay, so this direction is given by proposition part 2, and And then going backward is given by proposition part 3. Okay. And then what else? Oh, we haven't checked one thing, right? So we haven't really checked one thing here. So we need to check that actually they are bijection. Okay, so we have to check bijectivity here. Okay, we need to check bijectivity here. So we need to check that phi of phi hash inverse is actually bijective on group. Okay, on group, on subgroup. And you need to check this. Is it easy to see or not? Is it easy to see? So you know, you need to show 2 things here, right? Actually, there are 4 inclusions you need to show. There are 4 inclusions you need to show. Because each of them is a set equalities. So for each of them, you need to show 2 subset inclusion. Okay, so there are 4 things to check here. Okay. Are you comfortable with showing this subset inclusion? Or should we talk a little bit? Zhe no need. Okay. You try first. Okay, if cannot, then we can do it next semester. Next lecture. Okay. And then again, last thing you need to check. Okay, last thing you need to check. Phi inverse of script hash is equals to script hash times k. Okay, this one use Lagrange theorem. Okay, use Lagrange theorem. Try. Okay, I think there's only 2 things I didn't tell you how to prove. Is the bijectivity and this cardinality. I will write it inside my lecture notes. Okay, the proper lecture notes. If you cannot work it out, you don't understand, then we can do it together next lecture. Okay. Yeah, there's only 2 things I haven't tell you how to prove. Okay, this is a kind of big theorem. I'll make it. There's one assignment 3 question will use this. You will see how beautiful is this theorem using Sn. Okay. Thank you. Okay. See you next week.
Correspondence， 你所谓的 correspondence 是一个 map 还是一定是红绿灯？